Ahoy hoy, I'm Planner Walk, and Sabine Hossenfelder is someone who has been on my radar for a couple of years at this point, but maybe not necessarily because of the reasons that you might expect. Like, I'm not going to get particularly fussed if someone says that flat earthers are wrong, but not stupid. I would have a problem with it if they were to say that flat earthers were right, but so far that hasn't happened. The video that made me rather skeptical of Sabine is a video from a couple of years ago where she talks about particle physicists, and that is of course the video that we're going to be looking at today. Now, some people might point out that I am not a physicist, and Sabine is, so who am I to say that Sabine is wrong? But I have a solution to that. I talked to a couple of scientists. Now, one of the scientists I talked to was a physicist while the other wasn't. The person who wasn't says that it sounds like Sabine is misrepresenting what particle physicists actually have to say.
The standard model contains about 24 numbers that must be determined by experiment. One of them is known as the theta parameter. Experimentally, it's been found to be 0 or so small it's indistinguishable from 0. That the theta parameter is 0 or very small is known as the strong CP problem. It isn't really a problem because the standard model works just fine with simply setting the theta parameter to 0. But particle physicists don't like small numbers.
The reason why she felt like that was a misrepresentation is because in science, it's very hard to get away with the excuse of, oh, I don't like things being that way. Usually there has to be some kind of justification for why you think there's something else at play. Now, Sabine does go on to say this.
But particle physicists are somewhat more accepting. They accept small numbers if there's a mechanism keeping it small. The standard model has no such mechanism.
But the problem there is that she's not actually explaining why particle physicists don't like small numbers. And without that kind of context, viewers might assume something along the lines of, oh well, particle physicists are just being superstitious about small numbers. However, from the research that I've done, it appears that the problem isn't so much that the number is so small, it's that it is so precise. The reason why this is considered a problem is because most parameters in the standard model don't actually need to be that precise in order for the standard model to work. So of course, when physicists see a parameter that is so finely tuned when all the others aren't, they ask, why? Now, of course, I might be misunderstanding things here because I am not a physicist, but that does seem like a much more reasonable explanation than, oh, particle physicists just don't like small numbers. And when it came to the physicist that I spoke to, he also had disagreements with Sabine's video, and I'll be sharing those later on. So even though I'm not a physicist, I have spoken to one, and I seem to at least be partially correct in seeing that Sabine's video is flawed.
The list of things that particle physicists said should exist, but that no one's ever seen, is very long. No supersymmetric particles, no proton decay, no dark matter particles, no WIMPs, no axions, no sterile neutrinos. There's about as much evidence for any of those as for Bigfoot.
And that is a part of science. You go back far enough and you have scientists saying, well, the ether should exist. But then experiments were done and they found that there is no ether. And later, Einstein came along with relativity and showed exactly why we don't need an ether. You can also talk about how scientists used to say that there should be a planet called Vulcan orbiting the sun. And after looking for it, they could not find it. And later, Einstein came along with relativity. My point is that scientists get things wrong all the time because they don't have all the answers. If they had all the answers, then there wouldn't be a need for science.
In the 1970s, particle physicists completed what's now called the Standard Model. The Standard Model of particle physics collects all the fundamental particles that matter is made of and their interactions. When the model was completed, not all these particles had yet been measured, but one after another they were experimentally confirmed. The last one was the Higgs boson, which was found at CERN in 2012. It was the final nail in the coffin of the Standard Model. There are no more particles left to look for.
So humans have gone ahead and found all the particles that exist within the current standard model. But as the physicist that I spoke to pointed out, the standard model is not a fixed thing. This means that if there were a new discovery, let's say a new particle was found, then it is very likely that that particle would just become a part of the standard model. After all, the standard model does work very well, so it's easier to slightly modify it than it is to just completely replace it.
Already in the 1970s, they said that the standard model wasn't good enough because it collects 3 different fundamental forces. Particle physicists wanted those to be unified to one force. Why? Because that'd be nicer. Theories which combine these three forces are called grand unified theories.
Well, it could also help explain stuff where the standard model falls short and where a unified theory makes more sense. In fact, the physicists that I spoke to mentioned that in the early universe, the fundamental forces do appear to unify due to an increased temperature. Now, it may be that unifying all the forces is unnecessary and it can be figured out how it works with three forces. But that still requires a change to the standard model. So if that kind of change is required, then it seems like a unified model might be a good place to start.
Grand unified theories, GUTS for short, reproduced the standard model in the range that it had been tested already, but led to deviations in untested ranges. Grand unified theories made a prediction, which is that one of the constituents of atomic nuclei, the proton, is unstable. Starting in the 1980s, experiments looked for proton decay. They didn't see it. This ruled out several models for grand unification, but you can make those models more complicated so that they remain compatible with observations. That's what particle physicists did. And that's where the problems began.
So initially, this may seem pretty bad, because I have seen what flat earthers do in order to avoid admitting that the Earth is a globe. If you ever show evidence to a flat earther that their flat Earth model is wrong, they will change their flat Earth model in order to fit with that evidence so that they can still say that the Earth is flat. You know, flat earthers will say, we see too far, therefore the Earth must be flat. But when ships disappear bottom first over the horizon, that's because of perspective and foreshortening or something like that. However, there is a big difference here, because flat Earth is not trying to answer some unanswered question. The question it's trying to answer is a question that has already been answered ages ago, just flat earthers are unaware of that. Grand unified theories, on the other hand, are actually trying to answer questions that we don't quite have the answers for, like, how did the early universe work? The standard model in its current form does not quite explain that, so people are looking for different models to see if they can explain that. And even though at the present time there is no evidence to support the existence of grand unified theories over the standard model, it still remains an avenue that could hold some answers. Because as mentioned earlier, we don't have all the answers, even with the standard model as it currently is. Anyway, we're going to skip over a bit of her video that we've already talked about, which is to do with the theta parameter. But keep in mind that it is relevant to what she is talking about, the axion.
Particle physicists added a mechanism to the standard model that it forced the parameter to be small. But a consequence of this modification was the existence of a new particle, which Frank Wilczek called the axion. Unfortunately, the axion turned out to not exist. If the axion existed, neutron stars would cool very quickly, which we don't observe. But physicists didn't give up on the axion. Like with grand unification, they changed the theory so that it'd evade the experimental constraints. Lots of experiments have looked and continue to look for these invisible axions. None was ever detected, but physicists still look for their invisible friends.
So the thing about axions is they are trying to answer a question. Why is the theta parameter so small? But it's not just that question that they can potentially answer. They could also be a candidate for dark matter if they turned out to exist. Of course, you can ask, well, if you haven't found it, why do you keep on changing it and looking for it again? But then that brings up the whole thing of, well, how do you propose we solve the problem that it's trying to solve? So far it seems like the best that Sabine has is, well, these aren't actually problems that need to be solved. In fact, she pretty much says that.
I believe the reason they don't notice what they're doing is that they have invented all these pseudo-problems that the complicated models are supposed to fix, like the absence of unification or some parameters being small. These aren't real problems because they don't prevent them from making predictions with the standard model. They are just aesthetic misgivings.
But the problem with her saying, oh, it's not a problem, is that there are actual problems that she is just completely ignoring here. Usually a really good solution to a problem solves more than just one problem, like with Einstein's relativity, and I think that's what particle physicists are trying to do. Anyway, I want to go to one of the most baffling points in her video where she talks about dark matter, because her take on that is interesting.
Then there are all kinds of dark matter particles. A type that's particularly popular is called weakly interacting massive particles, WIMPs for short. Each time an experiment came back empty-handed, particle physicists claimed the particles were a little bit more weakly interacting and said they needed a better detector. There are headlines about this literally every couple of weeks. The Panda X4T experiment looked for light fermionic dark matter. They didn't find it. The Stereo experiment looked for sterile neutrinos. They didn't find them. CDX didn't find light WIMPs. Hess didn't find any evidence for WIMP annihilation. The microscope experiment didn't find a fifth force. An experiment called Sense Light didn't find sub-GeV dark matter, and so on.
You see, when it comes to all the different things that she was reading out there for the different attempts to find what the source of dark matter is, you'll notice that they were all different hypotheses, or at least most of them were. Sure, they all came up empty-handed, which I'm sure was her point, but we have no idea what dark matter is. Of course there are going to be a lot of failed attempts to try and work out what this thing is. And you can't just brush this off as, oh, it's not actually a real problem. Well, that's what I'd think at least.
One final objection I want to mention usually doesn't come from particle physicists, but from people in other fields who think that we need all these models to explain dark matter. But that's mixing up two different things. We need either dark matter or a modification of gravity to explain observations in astrophysics and cosmology.
So it is true that maybe dark matter is a result of our model of gravity being incomplete. That is a possibility. And the thing is, there are actually people working on different models of gravity to try and explain dark matter without dark matter. One of the most popular ones that I've heard of is something called modified Newtonian dynamics, or MOND. But it does have its own problems. For example, it's very hard to distinguish between MOND and a model based on dark matter. But that being said, whichever one you think is correct, there is still a lot of work to be done, and I don't think it's a good idea to just focus on one of them.
But if it's dark matter, then the only thing we need to explain observations is how the mass is distributed. Details about the particles, if they exist, are unnecessary. What particle physicists do is guess these unnecessary details. They guess, for example, that those particles will be produced at some particle collider, which then doesn't happen.
What do you mean the details are unnecessary? If there is extra mass in galaxies, I would very much like to know what it's made of. Like, correct me if I'm wrong on this, but as far as I'm aware, mass doesn't come from nothing. There has to be something there for the mass to be there. Like, sure, maybe she's correct and we'll never find it at a particle collider. But I'd rather at least attempt to try and find out what it is.
They say it's good science because these hypotheses are falsifiable. I'm afraid most of them believe this. But just because a hypothesis is falsifiable doesn't mean it's good science. And no, Popper didn't say that a hypothesis which is falsifiable is also scientific. He said that a hypothesis which is scientific is also falsifiable. The best way to see that what particle physicists are doing isn't good science is by noting that it's not working. Good scientists should learn from their failures, but particle physicists have been making the same mistake for 50 years.
Well, there's a couple of things. The first is that it's not like no progress has been made in the last 50 years. After all, it was only in 2012 that the Higgs boson was discovered. But also, there have been some observations, even some recent ones, which the standard model doesn't quite explain. An example that the physicist that I spoke to gave is that recently it was discovered that neutrinos have mass, and the standard model originally had neutrinos as massless. This means that particle physicists have been making discoveries. Yes, there's been a lot of failure to try and find certain particles, but that's to be expected. As I mentioned earlier on in the video, there has been failure to find all kinds of things that scientists thought should exist. And I do think that we're at a point in time where a lot of the easy questions have been answered, but we still know that there is more that we need to find out. So people are going to get things wrong as they try and find that out. Getting things wrong is a part of science. What matters most is that you accept the evidence.
There are some common replies that I get from particle physicists. The first is to just deny that anything is wrong. Because, hey, they are writing so many papers and holding so many conferences. Or they'll argue that it sometimes just takes a long time to find evidence for a new prediction. But both of those objections are beside the point. The issue isn't that it's taking a long time. The issue is that particle physicists make all these wrong predictions, and that they think that's business as usual.
Well, as I said earlier, you are going to get incorrect predictions. That is simply a part of science. I mean, if you have two competing hypotheses, at least one of them has to be wrong. But here's the thing that happens when you test predictions that turn out to be false. You narrow down the search. After all, there are plenty of unanswered questions out there, and if we're going to find out what the answer to some of these are, then we need to start ruling out possibilities.
The next objection they bring up is normally that, yes, there are all those wrong predictions, but they don't matter.
Oh hey, that's the objection that I just had.
The only thing that matters is that we haven't tested the standard model in this or that range, and we should.
Well, that's not really what matters to me, although I'm not a particle physicist, so maybe I don't know what really matters.
The problem with this argument is that there are thousands of possible tests we could do in physics, and all of them cost money, sometimes a lot of money. We must decide which tests are the most promising ones and the ones most likely to lead to progress. This is why we need good predictions for where something new can be found, and that's why all those wrong predictions are a problem.
So in a way, I kind of agree with Sabine here. It is important to allocate funds, especially when funds are limited, to things that are promising. Though I would go one step further and say that maybe more funds should be allocated to research that improves people's quality of life. But that doesn't mean that we can't fund other things like physics as well. But that being said, I do think an important part of working out where to allocate funds is to work out which questions are the most important questions to answer. And because of that, the amount of wrong predictions that people make isn't necessarily the most important thing to consider. One of the more important things to consider is, how important is it that we answer this question? In the case of dark matter, that does seem to be a very important question, and maybe it will take a while before we find it. But we're not going to find it by saying, well, too many incorrect predictions, let's stop looking. And another thing is, it can be tricky to work out what exactly is the best thing to fund. Do you go for something novel, something that's a bit more risky, or do you go for something that's a bit closer to what might be expected but is built on top of something that was previously shown to be false? Again, we're dealing with things that we don't know about, because if we knew about it, we wouldn't have to do science.
Another common reply I get from particle physicists is that it doesn't matter that those models are all wrong, because while they're working on it, they might stumble over something else that's interesting. And that's possible, but it's not a good strategy for knowledge discovery. As I've already said a few times, it does, as a matter of fact, not work.
I mean, it is certainly possible that you discover something interesting, but I'd also argue that that is the case for pretty much any science that you do. You can discover something interesting that you didn't expect. I mean, after all, that is how we ended up with certain types of pills. It was supposed to be heart medication, but people had other ideas of what they could use it for. So yeah, that line of reasoning is more of a defense of science in general, not just particle physics. Though given the state of things, I do think that we need more defenses of science in general.
Another objection that particle physicists often bring up is that this guessing worked in the past. But if you look at past predictions in the foundations of physics, which turned out to be correct, and that did not just confirm an existing theory, then it was those which made a necessary change to the theory. The Higgs boson, for example, is necessary to make the standard model work. The point is that we can learn from this. It tells us that a good strategy is to focus on necessary changes to a model, those that resolve an inconsistency with data or an internal inconsistency.
So kind of like how people have been trying to work out what dark matter is, because I don't know about you, but that seems kind of necessary. It's a big missing piece of the puzzle. And as I mentioned earlier, there are areas where the standard model falls short. So clearly there's some kind of necessary change. The problem is we don't know what the necessary change that needs to be made is. And the tricky part is working it out and confirming it. But I feel like I'm repeating myself here, because the whole point, I think, has been that science isn't easy, and I don't think it's useful to pretend like it is in any way. Sometimes when you're looking at a problem, it's a lot easier to try and say that the problem isn't a real problem than it is to actually solve that problem. And I don't think that it's really all that productive to make a YouTube video saying, oh, well, these problems, they're not actually problems, don't worry about it. Especially since the people that you need to convince are particle physicists. And as far as I'm aware, they usually don't consider YouTube videos to be serious academic critique. You'd be better off writing a paper. But anyway, that's where I'm going to end the video. Overall, I think that Sabine doesn't quite understand what particle physicists are trying to achieve, or their reasoning for it. I think if she understood it and was actually correct about what she was saying, then she would be able to convince particle physicists to do things differently, but apparently that does not seem to be the case. But let me know what you think in the comments. Do you think that I'm wrong about things because I'm not a scientist, or do I actually have a point? But leave a like and subscribe if you like this video. I will see you in the next video. Between you and me, I don't know if you can tell, but I really hate saying the word physicist. It is a difficult word for me to say quickly.